Welcome student. The video lecture 1 we are going to discuss in terpenoid citral. I am Dr. Devangar Pandya from Department of Chemistry, St. Xavier's College Autonomous, Ahmedabad. Let's begin with the introduction of citral. As you can see, this is the structure of citral. Citral is the most widespread and industrially very important member of the acyclic terpenoids. Citral is widely distributed and occurs as a principal constituent of lemongrass oil, which in lemongrass oil it is in the 60 to 80% citral is going to be obtained from lemongrass oil. It is optically inactive oil with lemon-like smell. It is mainly used in the preparation of beta anion, which is mostly used in perfumery products. The UV, IR and NMR data for citral is given over here. Constitution of citral. Here you can see the molecular formula as determined by elemental analysis and molecular weight determination is C10H16O, and on bromination it forms a tetrabromo derivative. Bromination it forms tetrabromo derivative indicating the presence of two double bonds. Here on bromination in presence of carbon tetrachloride, we're going to get tetrabromo derivative of citral. Presence of double bonds has been confirmed by hydrogenation as well after bromination, and citral forms tetrahydroderivative. Here is the reaction. On reacting with H2PD, on heating it will going to give you tetrahydrocitral. Third is the nature of oxygen. The oxygen present in the group, it forms monooxime with hydroxylamine. This shows that it contains a carbonyl group, and it reduces tolerance reagent indicating the presence of an aldehydic group as well. The presence of aldehydic group is further proved by its oxidation to gyranik acid having the same number of carbon atoms as citral has. Here is the reaction C9H15CHO on treating with silver oxide in presence of NaOH, that is our tolerance reagent, will going to get gyranik acid. The presence of alpha beta unsaturated aldehyde groups. The presence of an alpha beta unsaturated aldehyde in citral is indicated by the UV adsorption maximum at 235 nanometer. The nature of citral as terpenoid. Citral has the molecular formula C10H16O. It contains two double bonds with 4 proton and one aldehydic group with 2 proton. Thus, the molecular formula of parent saturated hydrocarbon is C10H22, and therefore it has a general formula of hydrocarbon as CnH twice N plus 2. Hence, citral is an acyclic terpenoid. On heating with potassium hydrogen sulfate, citral is dehydrated and cyclized to p-cymene. So here citral on treating with potassium bisulfate, on heating with that it will going to give us p-cymene. Formation of this p-cymene confirm that citral has this carbon skeleton of C10. So this is the carbon skeleton present in 2-citral, that is proved by this reaction. On oxidation of citral with alkaline cheminophore followed by chromic acid afforded acetone, oxalic acid and levulinic acid. Here citral treating with alkaline KMNO4 followed by its oxidation with chromium oxide will going to have 4-oxopentanoic acid, that is also known as levulinic acid, acetone and oxalic acid. Citral on ozonolysis gives acetone, glyoxal and 4-oxopentanal, that is the aldehyde form of levulinic acid, that is levulinic aldehyde. The formation of oxidation products can be explained if citral has this structure too. This structure, if this structure citral has, then we can explain the formation of oxidation, and the oxidation process is like this one. On oxidation with KMNO4 followed by chromium trioxide, we're going to get this carboxylic acid and acetone and oxalic acid. On ozonolysis, we're going to get these three fragments. Structure 2 on the citral explain all the above observation from 1 to 7, and thus the structure of citral is confirmed as structure 2. This structure of citral is further supported by its dildolization to acetaldehyde and 6-methyl 5-heptane to 1. This is the aldehyde hydroxyl group or treated with base, boiled with base. We are going to get 6-methyl 5-heptane 2 on and methanaldehyde or acetaldehyde. Dildolization is given by alpha beta unsaturated carbonyl compound. This reaction is known as Varennes-Tap reaction, which take place in the presence of NOH or KOH under boiling condition. The reaction take place as this one. You can see here the double bond shifted on oxygen, this double bond shifted on this carbon. As the double bond shifted on oxygen, the carbon become slightly delta positive and the base will going to provide electron to this carbon, so hydroxyl group will going to attach over here. So this is a conjugate addition of base, and then again you can see the electron on oxygen will going to overlap between carbon oxygen, so this pi bond will going to repel and it will shifted on this carbon. So treating with H2O will going to get this arrangement, then this bond will break and electron will shift to this CH2 carbon, and then proton is going to be liberated from here and it's going to attach with this carbon. So we're going to get acetone over here. Finally, the structure of citral has been confirmed by its synthesis. We have two schemes. Here I am going to explain the first scheme, the elegant synthesis of citral by this scheme 1. In the scheme 1, we can see here that a formation of carbon nucleophile would be there. So first step would be this. We're going to get the formation of carbon nucleophile, that is obtained by treating this acetaldehyde group with sodium ammonia. We're going to get this kind of nucleophilic carbon. The carbon nucleophile gives nucleophilic addition with acetone, partial reduction of alkyne to alkene, then allylic substitution reaction. Then after carbanion of ethyl acetate gives SN2 reaction with allyl bromide, like this one. Then in a 6th step, beta ketoester converts into beta keto acid on hydrolysis. Then beta keto acid on heating undergoes decarboxylation. Ketone react with Grignard reagent to form tertiary alcohol. Partial reduction of alkyne into alkene. Step 9, allyl rearrangement, and then we're going to get citral. So this is that scheme 1. To synthesize this compound, we have this acetylene treated with sodium ammonia to get nucleophilic carbon. That treated with acetone will going to get this attack. Then on reduction with H2PD BaSO4, or either treating with this will going to get this alkyl group converted into alkene. Then treated with PBr3 will going to get bromo derivative. On treatment with this will going to get this attack. On treating with base, that convert, and then we're going to get this kind of skeleton, and that treated with the Grignard reagent we're going to get this ether. On reduction with H2PD and BaSO4 we're going to reduce the alkyl to alkene, and then on treating with proton we're going to get citral. That is scheme 1. Now synthesis of citral by scheme 2. There are also different steps. Step 1 is aldehyde reacts alcohol in basic medium to form hemiacetal. Then alcohol undergoes dehydration in presence of acid to give allyl vinyl ether. The allyl vinyl ether on heating gives Claisian rearrangement. Then 1,5-diene on heating gives 3,3 sigma tropic shift, that is a cope rearrangement, and that scheme is like this one. So that way we can get the citral as well. Now isomerism in citral. The neutral citral is a mixture of two geometrical isomers. When the olefinic hydrogen on carbon 2 and methyl group on carbon 3 on the double bond are cis to each other, that isomer is known as a cis citral, which is also known as neral. And when they are trans to each other, that isomer is known as trans citral, and it is also known as geraniol. So these are the two cis and trans isomer of citral, neral and geraniol. Well, this is enough from my side. Thank you very much for paying attention to this video lecture. Keep asking question. As you know, asking question is a beautiful way to gain knowledge. Thank you.